Hi everyone, this is Gaurav from Classic Education online YouTube learning channel. And in the electrical circuit series, we will be having a very important numerical this time from two-port network. And this numerical came in GATE 2020 for electronics communication branch. And this particular numerical belongs to two-port network. And this numerical, we have to calculate the load impedance. And the case consideration is of maximum power transfer theorem. Hereby, in this question, Z11 is given 40, Z12 is given 60, Z21 is given 60, and Z22 is given 120. Okay. So, how to solve such numerical and what actually the answer is all about? Okay. So, first of all, what is the key objective of maximum power theorem? The, in maximum power theorem, we have to identify the load impedance, okay, such that power can be maximum delivered from source to the load. So in this particular numerical, hereby we are having a DC source whose frequency is, as you know, that it is 0. So it means the impact of inductance or capacitance will certainly get nullified, and because in the case of inductance we know that it is j omega L and frequency is 0, so XL will behave as a short circuit and likewise capacitor will behave as the open circuit. So here we can say that ZL is basically RL. Okay, ZL is basically RL. It is a load resistance. Okay. Now how to relate these given values and how to find out the ZL in a resistive network? ZL is basically RL I said, and RL is basically R Thevenin. Okay. So in this particular circuit, we have to look after the value of R Thevenin. Okay. So let's look into the circuit diagram of this particular Z port network, and then we will be taking that equivalent circuit diagram with two KVL equations, very simple equations, and we can easily solve this particular numerical. So here is the electrical equivalent circuit diagram, okay, whereby you can see this thing that this is basically the input port and this is basically the output port, and in this what we will do, we will just place a 1 volt battery over here, okay, and this 1 volt battery will provide a current of I2. Okay, why we are doing this thing? Because I just told you earlier that when we are having a maximum power theorem and we are taking the derivative of power with respect to load resistance, we will get a condition like this, that is R Thevenin equals to load resistance. So to find out the value of load resistance, we have to calculate the value of R Thevenin. Okay, but when a circuit will have dependent sources like over here you just see this one and this one, R Thevenin, the procedure to solve the R Thevenin is basically to place a battery source of 1 volt, okay, and with respect to I2 current we will form a ratio like this. This is the battery source of 1 volt, and with respect to the current I2 which is delivered from this 1 volt battery. So if we are able to calculate the ratio of 1 upon I2, we can easily comment on the R Thevenin, and load resistance is equal to R Thevenin. R Thevenin, the only procedure to calculate R Thevenin is such that we have to place a battery of 1 volt and we have to consider the ratio of voltage and current like this. When we are having dependent sources in the circuit and independent sources as well. Okay. So what we will do? We will do a very important procedure. We will just short circuit this particular independent source and we will place a 1 volt battery over here, and we can easily calculate the value of 1 upon I2. So let's see the procedure to solve the value of R Thevenin. So here is the calculation part. So you just see I just short circuited this individual voltage source, okay, and I have placed 1 volt battery over here. So how I will calculate R Thevenin equals to, I have to calculate the value of V Thevenin divided by current, okay. So over here what basically I did, instead of finding out V Thevenin, I just placed a battery of 1 volt. So I can write 1 volt divided by I2 current. This value I have to calculate, and from this value I can easily calculate the value of R Thevenin. So let's see how I have just calculated. So here is the equivalent circuit diagram for the input port and the output port. So here is the KVL equation for the input port, that is 10I1 plus 40I1 plus 60I2, and from this I have calculated the value of I1, so that I can place this value of I1 in the equation of output port and replace the value of I1 out there, so that I can get an equation in terms of voltage and I2 current only. So this is the equation for the input port. Likewise I just wrote down the equation for the output port, that is 1 minus 120 I2 minus 60 I1 equals to 0, and from equation 1 I just put the value of I1, and from this I get this expression, that is 1 minus 48 I2, okay, and from this I have calculated the value of 1 upon I2, and 1 upon I2 comes to be 48. So this 1 upon I2 is basically R Thevenin, and in the case of maximum power theorem, when we take the derivative of power with respect to load resistance RL, so thereby we will get expression whereby R Thevenin equals to RL. So in this question the answer is 48 ohms, and this is the procedure for the two-port network. Very easy method, and here we are not touching any dependent source. All the dependent sources are intact. These two dependent sources are intact. We haven't touched them. Only what we did, we just short circuited the voltage source, which was basically the independent source, and if there would be a current source, it will get open circuited. So this is the concept for two-port network, a very important question from GATE 2020 for EC branch. Thank you.